let's do this. So 3.4, we're talking about velocity, and that's one form of rate of change, and then we're going to talk about other applications as well. Okay, we've now said this over and over and over and over again. At this point, there is no excuse for you guys to not recall this information, but the instantaneous rate of change, right, one last time, it's where it's where you measure the slope of the tangent line at a specific point, right? So this is where we bring 2 points closer to each other so that the secant line becomes a tangent line, and so on and so forth. And we now know, like we know our name, that this is the formula for instantaneous rate of change. And with our new notation, this is now F prime, meaning rate of change at A. So the rate of change at a specific point.
Can you use the other equation that we had?
The other definition,
Yeah.
Correct. Yeah. So this is the most formal definition, and that's sort of a modified definition. Okay, so one example we're going to use this, and we're going to use to apply this, is a situation where we have enlarging circles. All right. So here's the question. Find the rate of change of the area A of a circle with respect to its radius r. So let's just envision this for a minute. Find the rate of change of the area of a circle. So imagine a circle which is changing in area. So it's expanding or, getting smaller. We want to find the rate of change with respect to its radius r. When you see the words with respect to, that means your answer should have that variable in there. Okay? All right. We need to find the rate of change of the area. That means you start with an expression or a formula for that quantity that you want to find the rate of change for. So, area with respect to r, right? Make it look like a function, a of r, like f of x, for a circle is pi r squared. Now, what is the name of my function here? What's the name of the function? A. What's the variable used in the function? R. So, if I had f of x, that's the name of the function. That's the variable. So, now I want a prime of r, that's the rate of change, equals this. And now I just need to take a derivative of this using my power laws. The 2 will come down. 2 times pi, pi is a constant, r to the power of 1. That's all you need to do. Okay? What this is the change in area with respect to the radius. Okay. So now, evaluate the rate of change of A at r equals 5 and r equals 10. So the way we do this is A prime of 5 is 2 pi times 5, 10 pi. A prime of 10 is 2 pi times 10, 20 pi. Okay, that's that. But as we know, coming up with the answer is never what it's all about. What does this mean? Let's analyze this for a minute. This is the rate of change of the radius, of the area when the radius is 5. Okay, so we got 10 pi. In more concrete, like in decimals, how much is 10 pi? 31.4, right? 10 times pi, 31.4. So when the radius, listen, when the radius is 5, it's changing at a rate of 31.4 units. Okay? when the radius is 10, it's changing at a rate of 62.8. So what does that mean? If I have a small circle with radius 5, it's changing at a rate of 31.4. But once it gets bigger, it's to a radius of 10, it's changing at a rate of 62.8. So what's happening? As the radius is getting bigger, the area is changing faster and faster and faster. It's like somebody would grow, let's say, 1/8 of an inch every year. And then once they hit, 7 years old, now they grow 1/4 of an inch every year. Then they get to 10 years old, now they're growing an inch every year. Then, like they're 15, now they're growing 1.5 inch every year. So their age or, like their height is changing how fast they grow, right? So I'm getting you guys used to some terminology. In a situation like this, we say is changing at a changing rate. Does that make sense? Okay. Now, here's important. This is okay. So if R is measured in inches and dA in square inches, so what is the appropriate for dA dr? Remember, A prime of R is the same as dA dr. The way I see this is A prime is the change in A with respect to the change in R. Now, if R is measured in inches and A in squared inches, the change in A is inches squared, the change in R is inches, and that's all. Inches squared per inch is the unit. You don't cancel them out and say inch, okay? So the area is changing in this first case at a rate of 10 pi square inches per inch of radius. Then it's changing at a rate of 20 pi square inches per inch of radius. You could say that. You could say that. Whenever the rate is changing, yes, there is acceleration. If this was a moving object, yes.
Changing slope is changing acceleration.
Right, right. Okay. So let's move on then into motion along the line. Okay. So let's just define some variables here. Suppose an object is moving along a coordinate line, like an axis. We're going to use the variable s. So instead of x-axis, we're going to call it an s-axis, so that the position is going to be given to us as s of t. Okay? So the name of the function is s. The variable is t, and s will be position. X is just used for so many things. Now, displacement, okay, of the object over the time interval t1 to t2 is s of t2 minus s of t1. So please, please, please remember, this is the final position minus the initial position. You can't mix up the order because this is dependent on direction. Okay? Average velocity is displacement over time, which means final minus initial over the distance, over the difference in time. Okay? So, is there any calculus here? No. Okay? There's no calculus there. When we get to instantaneous velocity, yeah, that's where. So, average velocity, you take a road trip. 200 miles takes you 2 hours, right? You were driving really fast, 100 miles an hour, right? Instantaneous velocity, if somebody called you up and said, hey, how fast are you going right now? And you looked at your speedometer That's your instantaneous velocity. You may be going at 70, 80, 100, who knows, okay? The instantaneous velocity is the derivative of the position function, all right? The derivative of the position function. And so V is S prime of t. Okay. This can either be positive or negative. That's the velocity, because it also, velocity is a vector quantity. Remember, it has speed and direction. Now, speed is the absolute value of the velocity. So look at, do you see the difference? You find v of t, then you take an absolute value, that's speed, and speed is always positive. It's like length. Right, it's speed. It's like, it's not a vector quantity. How fast are you going? 70. That's it. There's no direction. It's a scalar. Good. Okay, now acceleration is the rate of change of velocity. Meaning, how fast is the velocity of changing? So, acceleration is the derivative of the velocity. So, acceleration is v prime of t. So, how do we get v prime? How did we get v of t? It was s prime of t, right? So, acceleration is also s double prime of t. So, you have position. You take a derivative, you find velocity. You take a second derivative, you find acceleration. Okay? Now, acceleration is a vector quantity, can be positive or negative. I know, but I want to make sure that you don't miss some of these things.
Yeah, sorry.
Okay, so speeding up and slowing down. You see these questions so often in the AP calculus tests. Speeding up versus slowing down. This is the quickest way of figuring this out. When velocity and acceleration have the same sign, the object is speeding up. Okay? You're going in the negative direction, you have negative acceleration, speeding up. When velocity and acceleration have opposite signs, the object is slowing down. Okay? All right, so let's do this. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of this after t seconds. So this is your S of t. Those of you taking physics, this is the equation for free fall, right? In feet, it's negative 16. Yeah. In meters per second, it's negative 9.8 t. Right, always. Okay, so it is going up with a velocity of 160 feet per second, which is about 109 miles per hour. It reaches this height after t seconds. Okay? So this is its position. Okay, the question asks, how high does the rock go? All right. This is going to go straight up, and then at some point, it's going to come back down, right? So, when you shoot it up, you give it an initial velocity of, what was it, 160. So, as it goes up, the Earth is trying to pull it down. So it slows down, slows down, slows down, slows down. At this very instant, at the very top, momentarily, like a a tiny fraction of a second, its velocity is 0, then the velocity starts to increase again. Okay? So when a projectile is going up and then down, at the very top there is a split second where the velocity is 0. So here, velocity is 0. So if I find the time when the velocity is 0, I can use it to find the position at that time. So, v of t is equal to 0 at the top. Now, what is v of t? Well, that's s prime of t. And what's s prime of t? I need to find the derivative of this function. So that's 160 minus 32t. Okay? Now, I want to set this equal to 0. So 32t is 160, meaning t is about 5 seconds. So it takes 5 seconds for it to reach up, and then it's going to come back down. At t equals 5, there is a split second where the velocity is 0. So now my question is, where is it at t equals 5? If s of t is describing the position at any given time, then when I plug t equals 5 into s of t, that should tell me its position at t equals 5. All right? So I say s of 5 is equal to 160 times 5 minus 32 times 5 squared. That's 400 feet. Waiting. S of t.
So would it be 16 times 5 squared?
Oh, 16, sorry. You still get 400. So here the velocity is 0, and we just found out that the maximum height is 400 feet. Okay, what is the velocity and the speed of the rock when it is 256 feet above the ground on the way up and on the way down? So this reaches a maximum height of 400 feet. Now I want the velocity when it's 256 feet up on the way up. I want the velocity there. And then when it comes back down, I want the velocity there. Okay? So, I need to know what was the time when it was at that height first, and then what was the time when it was at the same height second. So, yeah.
Are you like equations from like something that you could do?
No, you should stick to here. Yeah. But you have all the information here. I know that S of t is 160t minus 16t squared. That's my position function. I want the position to be 256. Okay? So I'm looking for the time when it's at 256 feet. Let's move everything over. So this is, I'm also going to divide by negative 16 on the way, all right? So I'm going to get t squared minus 10t plus 16. So I divided and so on. When I factor, I get t minus 8, t minus 2. So t equals 2, t equals 8. Isn't that cool? So what does that mean? Look, at t, when was it here? At the very top? At t equals 5. So now I know that at t equals 2, it's at 256 right here. Then at t equals 5, it reached the maximum. Then at t equals 8, now it's falling back down and passing the same point again. Isn't that cool? That's super cool. So now I need to know what is the velocity when it's at t equals 2 and what is the velocity when it's t equals 8. So I say on the way up, I need to know v of 2. So it's 160 minus 32 times 2, 96 feet per second. No, this is the velocity. The velocity, v of t. And then the speed is the absolute value of this, so 96 feet per second. On the way down, it's v of 8. 160 minus 32 times 8. Again, 96 feet per second. I'm sorry. This time, negative 96 feet per second. But the speed is 96 feet per second. So, when it's going up, it has a speed of 96 feet per second. At the same point down, it's got a speed of 96 feet per second. The speed is symmetric the entire way down, up and down. Okay? So it starts at 160, and then it's like 100, and then it's like 96, then 50, 20, 0. Okay? But the velocity on the way up is positive 96 because it's going in the positive direction. And then on the way down, it's negative 96 because it's going in the negative direction. Okay? Speed is the absolute value. All right. Acceleration of the rock at any time t. Acceleration is v of t. I'm sorry, v prime of t. My velocity was 160 minus 32t. Now I need the derivative of this, which is just negative 32.
That's not the actual acceleration. It should be. It was a real thought.
No, it is.
It would be 9.8, right?
Meters per second squared, but this is in feet.
No, I was just curious if when we convert that to
Yeah.
meters per second, if it would be the right.
Yeah, because it's the same. It's the correct formula. So, the acceleration is negative 32 feet per second, so it's feet per second squared. Okay. D, when does the rock hit the ground? Yes.
So I think what we do is you say that would mean position 0. So
Right.
plug in 0 equals 160 minus 60 squared.
Right.
Then after that,
You factor it out.
And you get t equals 0 and t equals 100.
10.
Yeah. 10, and that's your answer.
Exactly. Perfect. So, when does it hit the ground? It means it falls back. So now its position is 0. Right? So S of t is 0. And then it's algebra 2. Right? So I factor out 16t. So I get 10 minus t equals 0. T is 0. T is 10. So when does the rock hit the ground? At t equals what?
0.
Just t equals 10. Because t equals 0, you launched it up. It says when does the rock hit the ground? It hits the ground at t equals 10 seconds. Are we okay with this? Okay, listen up. If you write t equals 0 and t equals 10, it is not Correct.
You could cross out.
Right? So, okay, wait a minute. A couple of things here. A little bit of notation. You see how we did this? Look at how I have accurately labeled every single thing that I'm doing. So, if you do something like this, which I can envision a lot of you guys doing, this is just numbers. I don't know what that is. So please take care and label what it is that you're finding, okay? It's the difference between a sophisticated math student and somebody just writing stuff down, okay? That's AP caliber. That's college level caliber. Yeah. Correct. That's when you launch it. It's at the ground when you launch it, and then it hits back at t equals 10. Okay. Now, could we have predicted the answer to the last question? How?
Because we found the first question, we found how high does the rock go?
Yeah.
We found the time it takes to get to the highest point. So by definition, if it takes that time to get up there, it's going to take the same amount of time.
Exactly. All this is symmetric. If it took 5 seconds to go up here, it needs to take another 5 seconds to go back down. So a total of 10. All right? So ways to just sort of like check your work. Okay. A particle moving along a line so that its position is given by this function. Again, this is the position where s is measured in meters and t is measured in seconds. Okay. We're given domain here, right? What's the domain of this situation here? T is greater than or equal to 0. So keep that in mind, okay? Everything that we are doing is defined in that range. Now, obviously, you might say, well, duh, T is greater than 0 always. But in another case, it might be for T is greater than or equal to 5, in which case, like, you have to like be careful here, okay? Okay. Find the displacement of the particle during the first 2 seconds. All right, the first 2 seconds. Okay, so T1 is 0, T2 is 2. Okay, again, more than just getting the answers to these. I know maybe like a lot of you, 70-80% of you guys could reason this stuff out and come up with an answer. More than that, however, particularly for the AP Calculus exam, the way you write your notation makes all the difference. And when I grade, starting with this next assessment, I'm going to be grading like they will on the AP test. So you are going to be getting points off for little itty bitty notation stuff. And, the grade will fall where it falls, right? So make sure you stick with this notation. Yeah. I think so. Yeah. Okay. Displacement is S of 2 minus S of 0. Okay. S of 2, we're just going to plug that into S. We get -1 minus 3. So that's -4 meters. Okay, go ahead and find the average velocity during the first 4 seconds. Is there any calculus for that one? Yes? No? No. No calculus. It's algebra 2. Yeah, we just found S of 2, we have to find S of 2 and S of 0. So that's not the displacement, that's just the position at 2.
I did it wrong.
Okay. So, yeah, so, yeah. Yeah.
For average velocity, you just like V or like average?
Yeah, V is good. For the time being, let's just, yeah. For the time being, let's write average velocity until we solidify our notation. Fine. You can write V sub average. Don't write just V though, because that's V of t, that's instantaneous. So S of 4 minus S of 0 over 4 minus 0. This I need to see. Okay? After this, I'm good with just 0 over 4 equals 0. That just lost you points, because what are you missing? No? There's nothing left in between. In between, everything's good. Units, meters per second. So, okay. Find the instantaneous velocity. When you hear the words instantaneous velocity, derivative. All right? So, V prime, we need V of t. Okay, instantaneous velocity when t equals 4 technically is asking us for V of 4. Okay, so first I want us to find V of t. So we're just going to take the derivative of S of t. So V of t is S prime of t. Show this. Okay? Show this, because it's important that you convey, that you know that velocity is the derivative of position. This is calculus concepts. Equals to 2t minus 4. So V of 4 is 2 times 4 minus 4. So that's just 1/4 meters per second. Okay? The acceleration of the particle when t equals 4. Now I need to find A of t, which is V prime of t, which is just 2. So A of 4 is 2 meters per second. Show me all of this squared. Yeah. Actually, that deserved more. For me, that deserved like 3 out of 4 points.
3 squared?
Can you imagine? I like go and take points off from other problems. I should do that. Okay. Describe the motion of the particle. Okay. At what values u of t does the particle change direction? Okay. So what we need to do is, for this one, when it says describe the motion of the particle, you have to look at the velocity and the domain. All right, this is where the domain really comes in. So what you want to do is, when it says describe the motion, you have to say when is it moving in the positive direction, when is it moving in the negative direction. And we just found out that it switches between positive and negative direction, and in between switching from positive to negative and vice versa, there is a moment when the velocity is 0. So first we have to figure out when the velocity is 0. Okay, so my V of t was what? 2t minus 4. 0, yeah, is 2t minus 4. So now I want the time, or times, depending on the function, when the velocity was 0. So in this case, t is equal to 2. Okay. At this time, so this is the time when V is 0, which means it's the time when the particle is doing what? What is the particle doing at that time?
Switching.
Yeah, but it's momentarily stopped. Okay? All right. So now, this is important. Notation. Look up. You have to do a number line. Okay? This is 2. What was the domain? T is greater than or equal to 0. That means you have to show that as an endpoint to your number line. So here, you say that's an endpoint, and it's 0. This keeps going. You can put an arrow. You don't have to put an arrow, but don't put a vertical bar. You have to say, though, that this is V, so we know what we're talking about. So this is an expression for, remember how we used to do, did we do this last year? No. Okay. This is, okay, so this is my T equals 0 and T equals 2, right? So this is my velocity. So now what I have to do is I have to see in this range of 0 to 2 time, is my velocity positive or negative? So I pick a point like T equals 1. I plug it into velocity. 2 minus 4, that gives me negative, right? So V is negative there. After 2, V will be positive. Okay. I plugged in like a point from here, like 1 into here. And then I plugged in a 3 into here. So, what does this tell me? In the beginning, it's telling you that this particle is moving along a line. Okay? That implies that it's moving horizontal. So you can say, basically, the most general way of saying this is, from 0 to 2, the particle is moving in the negative direction. Now, from 2 and on, the particle is moving in the positive direction. Now, when it's saying, motion along a line, you can imply that this is horizontal, so we can say left or right. So, particle moves left, okay, when the time is between 0 to 2. Look here. Open on 2, closed on 0. Okay? Because at 2, V is 0. Then it's at rest when T equals 2 and it moves to the right when T is greater than 2. You can also add, it changes direction when T equals 2. Now, let me say one thing before I forget. Sometimes, suppose this was, 2t minus 4, parentheses t, right? Suppose, I'm just going to write it for a second and then erase it. Suppose it was like this. When else would it be 0? When t equals 0, right? That means in that situation, when the velocity is 0 here and here, I cannot close this at 0. You see that? Okay, because technically it stopped at 0 in that case. So watch out for that question. You could.
But you can't write it.
You could, but be very, very specific when you do that because now, okay, so when you say particle moves left when, or particle, if you say, don't erase this. If you say particle moves left on 0 to 2, this is not enough because you now haven't indicated that 0 to 2 is a time interval. So you have to say, yeah, particle moves left over the time interval 0 to 2. Like, do you see how specific you have to be? Another thing I wanted to point out to you is a little bit of grammar for you. I have defined any pronouns I have used. So here when I use a pronoun it, that pronoun has been defined here. It's the particle. You see what I mean? So don't leave your, like AP Lang stuff somewhere else and come here and make grammar mistakes. If this started with it moves blah, 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 like you have got to be super, super clear about these things. There is no it moves up. I don't know what that is. There is no it goes up. The particle moves in the positive direction, or the particle moves in the upward direction. Okay, let's move on. Yes.
Why would you not do the closed domain but when it also is 0 at 2?
No, when it's 0 at 0, I said. So in this problem, sometimes when your position function is like a cubic function, then you'll have 2 times when the velocity is 0. Because it goes like this. Oh. Okay. A particle P moves on the number line shown in part A. Part B shows the position of P as a function of time. Okay? So, this is the actual motion. This is like there's a little bead and it's going back and forth here. Somebody graphed it here. So this is the actual motion. There is an actual like particle here moving. There's like a little car moving back and forth. This is a graph. Okay? When is P moving to the left? Okay, so this is the position. Okay? All right. Yeah. Yeah. Here. Yeah. Okay. So, when is it moving to the left? Okay, when is it moving to the right? When is it moving still? So, moving left or right? This has to do with whether the velocity is positive or negative. So let's think about this for a minute. If it's moving left, it means v of t is negative. If it's moving to the right, it means v of t is positive. Let's think about that further. Hang on. What is v of t as far as the position is concerned? V is the slope of this. So now, if I say v of t is negative, it means slope of the position is negative. Okay? So, slope of s of t is negative. Here, slope of s of t is positive. So then when it's standing still, slope is what? 0. So here, it looks like m is 2. No, I'll talk. No. Yeah, hang on. Yeah, yeah. You guys are moving ahead. Hang on. So m is 0. Here, m looks like it's -4. M is 0. Here, m looks like it's -2. Okay. So, okay. So, it's moving left everywhere that there is negative slope. So, over the interval 2 to 3, right? 2 to 3. Just like before when you were like graphing the derivative, remember we closed the endpoint at the very, this is what you're asking, the very edge of the endpoint, Henry? The very edge and the very edge have to be closed. Everything in the middle has to be open. So 2 to 3 and from 5 to 6. So I leave 5 open but close 6. It's moving right. From 0 to 1. That's it. And then it's standing still. Where 1 to 2 and 5 to 6. No, sorry, 3 to 5. Okay, I want to tell you one other thing. So, we talked about what it means when when the slope is positive, 0, or negative. Now raise your hands for this one. Think about it for a minute. This graph is the position function. Some portions of this graph are above the y-axis or the s-axis. Some portions of this graph are below the s-axis. What does that mean? This is the position. What does that mean in terms of the particle? Raise your hands. I want to give you guys a second to think about this. Okay? Not just the slope, but what does it mean that the graph itself is above and below? Got 2 people. What do you guys think? Don't be afraid to share here. Well, it's moving backwards here as well. And here, okay? Yeah, not necessarily.
It starts going like on the other graph, like it's beyond 0.
Right. Okay. So that's what it means. So, when the graph is above, that means its position is positive. That means physically it's to the right of the center. When it's negative, its position is negative. It means physically it's here. So, some of the things, now we don't have too much information about this, but some of the things that we could guess, right? So here, when t is 0, s is 0. So it starts here. And then which way does it move? To the left or right? To the right. And then it's standing still, and then which way does it move? To the left. It's moving, okay, so it moves to the left. At t equals 2.5, it's at 0 again. At t equals 3, you see how the graph moves below? That means that's when it crosses the border here. It's still moving to the left, here, to the left. Then, what happens at t equals 3? It stops. 2 seconds go by, it's standing here, it's thinking. Then what does it do? It goes further this way. You see that? How cool is that? Super cool, huh? Yeah. Okay. So, graph the particle's velocity and speed where defined. Okay. Velocity is the slope. Speed is not, right? So, so slope from 0 to 1, slope is 2. From 1 to 2, slope is 0. From 2 to 3 is negative 4. And then from 3 to 5, it's 0. 5 to 6, it's negative 2. Is that there? Close the end. Okay. The only closed dots are this one to the very left and this one to the very right. These are open. It looks that way because it's on the, because it's on the mark. Then the speed. Speed is the absolute value. So if the velocity is positive 2, the speed is also positive 2. If the velocity is 0, so is the speed. Okay, from 2 to 3, the velocity is negative 4. What's the speed? Positive 4. And then 3 to 5 is 0. And then it's positive 2. Does that make sense? Or does that make sense? Okay, now, where is Pearson? Okay. So this stuff, let me see what they are, and then if it's something that I could do now, I'll do it. So this was 3.3. Number 23D. Oh.